We're going to take a look at the last types of volumes that we're going to do in calculus, which is volumes of cross section. One example you can see over here is if the cross sections were squares, it's kind of like a loaf of bread. If you took one of those pieces of bread, it would just be a square. Down here, we have an example of all kinds of things. You have squares here, triangles here, you have semicircles here, and you have rectangles over here. And over here, we have an example where the base is just a circle, but this is what the volume would look like if you used a bunch of rectangles, and this is what the volume would look like if you used a bunch of squares. So we're going to take a closer look at those kinds of examples in a moment. Here's our first example. We have some shaded region. Shaded region probably looks something like this. And for this example, our squares are going to have sides of different lengths. The closer you get here, the smaller the squares are. The closer you get to the outside, the bigger the squares are. So here's an example of what the volume might look like with only 4 squares. This one has 8 squares, and this one has 16 squares. So remember, those squares are different sizes. If we were going to do an integral to find the volume, we know that the area of one square is just going to be the side times the side. So we'll just say s squared. But then the volume, you see there's a little bit of a width here. We're calling that change in x. So if you multiply by that width, you actually get a volume. Of course, this is just the volume of one piece. If you wanted to get the real volume of the entire solid, basically what you do is you just do the area of one piece. That's what this is. Then you multiply by the height, which is kind of like your change in x. The dx is an infinitely small width, but it's not 0. And of course, we fill in all of these square prisms from A all the way to B. Let's look at some more examples. We just saw the example for a square. What if we had an isosceles right triangle, so the base and the height are the same? Well, really what we have here is just half of the square. So if you kind of look at the previous one, you can see we're going to have the same area, but with just a 1/2 in front of it. So here our volume is just going to be 1/2, and then the area of the square times our change in x. And our change in x is just our width there. So that's the volume of just one piece, just one of these. If we wanted to find the volume of the entire solid, we have to fill in a whole bunch of these triangular prisms, starting from A and going all the way to B. And if they were semicircles, well, the semicircle is one of the trickiest ones, because we say, well, what's the area of a semicircle? Well, pi r squared is the area of a circle, so half of that would be a semicircle. But then it gets a little trickier, because our shaded region looks something like this, and our s distance is just the top minus the bottom. So here's our s distance. However, to find the area of a circle, we need the radius. So really, we need half of our s. We just need this distance right here, just half. So if we look at that semicircle, the radius is really just going to be half of s. So that's pretty tricky, that the radius is 1/2 s. So we can trade our radius for 1/2 s before we square it. Now, if we square it, we're going to get 1/4. And there's another 1/2 on the outside, so our final answer is going to be 1/8. So that's a tricky one. Some people just memorize it. For a square, it's just 1 times s squared. For half a square, it's just 1/2 and then s squared. And then for a semicircle, it's 1/8. But it does have a pi s squared. Now what's interesting is it doesn't matter what the shape is. All you have to do is put the area of one piece, whatever that is. You put the area of one piece inside of the integral. So whatever one slice is goes inside your integral. And then you want to fill in all these slices starting from A going all the way to B. So your integral will just go from whatever the starting point is all the way to the ending point. And that'll be your volume. So the big challenge is always going to be to find the area of one slice. What is the area of one slice? Because that's what's going to go inside your integral. Now that slice is called a cross section, and that's why these are called volumes of cross section. Let's go ahead and do a real example. For our first example, we're going to have cross sections that are squares. So you can see the shaded region over here to the right. Let's look at what S would look like. S is going to be the top minus the bottom. So you can see the closer we get to the beginning, we have smaller s's, so we'll have smaller squares. And the closer we get to the end, we'll have bigger s's, so bigger squares. So our s is going to change based on what our x value is. But let's just focus on one square. Each side of the square is going to have this distance right here. I'm calling it S. And to measure that distance, it's just going to be top minus bottom, where the top is just a square root of x function, and the bottom is e to the negative 3x. You can see I wrote that over here. That's the length of one side of our square. So remember, we always put the area of one slice in here. The area of one slice is just going to be s times s. So I'm going to say s squared, because our cross sections are squares. And we are going to fill them in from t all the way to 1. So you can see my bounds go from t to 1. And one of these s's is the same thing as the square root of x minus e to the negative 3x. So let's plug that in. Okay, there we go. We plugged in our s. This is our s. And I want you to notice that it's squared. And again, our bounds went from t all the way to 1. So we're going from t to 1. And that's basically it. Now I do want to point out that each square is going to be perpendicular to the x-axis. The other type that we might do is if they're perpendicular to the y-axis, and that'll be our next example. So we'll show you that one in 1 second here. Okay, for our first example, we did squares, and now we're going to do rectangles where the height is 4 times the width. So our width is going to be this distance right here, but the height is going to be 4 times whatever that distance is. So our height is going to be 4s. So we have a rectangle, and we're saying that this distance here is just going to be s, and the height is going to be 4 times s. So if we want to put the area of one slice, it's going to be s times 4s. And so I think you can see that that's going to be 4s squared. And since that's the area of one slice, that's what goes inside my integral, 4s squared. Now you'll notice that each rectangle is going to be perpendicular to the y-axis. So we're going to need to fill these in all the way from 0 all the way up to 4. So our integral is going to go from 0 to 4. Now all we have to do is plug in our s. Now what is s? Again, it's going to be right minus left. The right side is just 2, and we do minus. Now in order to find the left, I'm going to have to solve it for x. So I need to do the square root on both sides. And that's going to give me x equals the square root of y. Remember, the positive square root of y is going to be the right side. The negative square root of y is the left side. I don't want the left side, so I'm going to go with the positive square root of y. So I can replace y equals x squared with x equals square root of y. And again, I'm doing right minus left, where the right is 2. Then I do minus, and the left is just going to be square root of y. And that's my s, and I can plug my s in and I'll be done. My s is going to be 2 minus the square root of y. There we go. That's my final integral. I want to point out that everything matches. This is dy. Our functions were functions of y, and our bounds go from y equals 0 to y equals 4. Okay, for this example, I do want to point out that we were perpendicular to the y-axis. So each rectangle was like this instead of going up and down. And on the previous example, let's take a look at that. You can see we were perpendicular to the x-axis, so each s went up and down. Now, how would this one be different if instead of squares, we had isosceles right triangles? So basically half of a square. Well, the only difference is that our formula would be 1/2 s squared instead of just s squared. So the only difference would be that we'd have this 1/2. So again, instead of having a square, we're talking about, well, what if you had half of a square, like a triangle, a right triangle? We're saying it's isosceles, so this side is the same as this side. They're both s. So one slice is going to look something like this. How would that be different? Well, the only difference is we just have to put a 1/2 right inside here. So each side is not going to change. It's still going to be the top minus the bottom. So the s is not going to change. For the square, we already saw what the answer was. It was going to be this right here. But if we had isosceles right triangles instead of squares, then each slice would just be half of the square. So you would get this extra 1/2 inside here, and that's the only difference. So that's how it would be different if we had isosceles right triangles instead of squares. So basically half of a square for each piece. Let's go back to number 2 again. How would number 2 be different if instead of rectangles, we had semicircles? Let's take a look at that. Well, first off, our s is not going to change. We're still going to have the same s. So our s is right minus left. So we're getting 2 minus root y. That doesn't change. But do you remember what the factor was for a semicircle? Let's go back and take a look. If you look inside here, we have 1/8 pi s squared. So that's kind of like pi over 8 s squared. So we're going to need pi over 8 and then s squared. Remember, each s did not change, so we can plug this in for the s. 2 minus the square root of y. There we go, we plugged in the s. And then we have our factor in front that belongs to a semicircle. Some people just memorize that, pi over 8 s squared. But that's basically it. So this different shape of semicircle, all it did was just give us a different factor in the front. Our s did not change. We had the same s, and it's almost always just going to be a number times s squared. For semicircles, that number is pi over 8. I do want to point out that sometimes you get them perpendicular to the y-axis, and that's when you're going to see a dy, a function of y, and your bounds are going to be y equals 0 to y equals 4. And if it's perpendicular to the x-axis, let's go back and take a look at that. Then you're going to get a dx, you're going to get functions of x, and your bounds go from x equals to x equals. So that's pretty much it. Now it's just time to practice a bunch of these. The more you practice, the easier they're going to get.